Hello, I'm Philip Hallam-Baker with the Komodo Group, and this is part 3 of my podcast series on usable secure email. In parts 1 and 2, we looked at the problem of email security and why previous solutions to the problem either haven't provided enough security or have provided too much security for people to be able to use them. And I've divided the solution to that problem up into two. One part, a research problem of how do we develop new trust models for enabling people to transfer trust on the internet, really interesting problems. And another set of problems, actually a larger set, of what I call plumbing, which are bread and butter issues like message formats, key formats, encodings, all the nuts and bolts of protocols where the actual solution chosen doesn't really matter so much as the fact that a choice is actually made and everybody goes to it. And the way that I've structured the solution is so that we have one set of plumbing that everybody can share, and multiple trust models can then be built on top of it. So instead of everybody who wants to secure, instead of what happened with PTP and S-MIME, and both groups developing their own message formats, their own mechanisms for sharing keys, and so on, when all they disagreed about was the trust model, we'll have one set of plumbing that will support either trust model. Our usability objective here, and I believe that it is the lack of usability that is holding us back on the security problem, a usability objective is frictionless cryptography, by which I mean that it must be absolutely no more difficult to use email securely than it is to use email now. So when you're sending a secure email, it must take absolutely no more effort than sending one today, insecurely. And by no more effort, I mean not just one more click, I mean no more clicks. The infrastructure is going to have to decide which mails have to be encrypted, which mails don't have to be encrypted, which mails must not be encrypted, and which keys to use if they're going to be encrypted. All that has to be taking place under the covers, because otherwise people are just not going to do the effort. The configuration steps are also going to need to be simple, and in fact we would like our email tools to automatically configure our mail clients for security. And when we're trying to support this, we're trying to support comprehensive functionality. So we want to support functionality like supporting the user who's lost their keys or has forgotten their passphrase or has lost a device that had an important decryption key on it. We've got to support all that functionality. But what we don't need to do is to support every imaginable feature. And in particular, we don't need to support every single cryptographic algorithm that some geek might like. One of the problems with security protocols is a thing called vanity crypto, where you have 100 different cipher suites that are defined in a specification. Not because anybody needs 100, but because there are 100 academics out there who've all done that work, all written their own cipher, and they'd like to see people be able to use it. So the way that I approach usability is a task-centered approach, in that I'm not a big fan of experimentation, because designing good experiments in usability is actually a lot harder than designing good usable protocols. Rather than looking at a secure version of a protocol and seeing whether a user can make sense of it, I'd rather be able to design the protocol in such a way I can prove that this new secure protocol looks, tastes, smells and feels to the end user just the same as the old one, and so they shouldn't have any difficulty with it because they're not doing any more effort. So the first task that we're looking at is configuration. How does a user decides that they want to be able to receive secure email? How do they configure their trust set so they can do that? They have multiple devices. How do they move their private keys onto those additional devices? If they lose a device, what happens? How do they tell the infrastructure, don't send encrypted messages so that device can decrypt them in future? And how do we manage all these exceptional events like, oh, I've forgotten my key, I've told Mallet my private key. And another issue that we've really got to face is if we're going to make these keys into personal keys, we have to have a way of dealing with the death of the key holder. In that, people should not be able to sign messages on somebody's behalf after they've died. One of the ceremonies in the installation of a new pope is the ceremonial destruction of the old pope's ring. And that was done so that they could show that no more papal bulls are being issued under the authority of the old one. The other thing that we need, the other set of tasks, is sending mail. And when we're sending mail, somebody has to decide, should the message be encrypted or not? Or rather, not someone, in that we don't want the user to be having to decide, should I click the encryption padlock or not? Because if you leave that choice up to the user, they're going to forget most of the time. We want to make it so that the user can just say to their email client, just encrypt by default. And the mail client will then send the message encrypted if at all possible. And if the recipient has said, oh yes, I prefer to have all my email encrypted, just send it to me, I can cope. Obviously with email clients that we have at the moment, somebody saying, just sending encrypted email to somebody just because they have a public key is likely to make you rather unpopular, because a lot of people like me are like me now, and they have a lot of machines that they read their email on. If you send them an encrypted mail, they can only read that mail if they take special effort to go to the machine that's got the decryption key. In architectural terms, this is called protocol architecture, and it has lots of similarities to traditional architecture. In architectural terms, this is a remodeling job. And just like the remodeling job they did on the Louvre, we want to make use of the existing work wherever possible. We want to make use of existing specifications, existing deployed code, and wherever possible, wherever it's necessary to take an existing specification and add a small amount of functionality, we're going to want to try and do that in the same idiom. If we're adding a feature to an ASN1 encoding message, we're going to do that in ASN1 or whatever. But where we're developing something that's a completely new functionality, we're going to do it in a modern approach, because that's what we do today, and that's what makes sense, and that's what the tools are designed around. In order to help people develop this system, I've developed a testbed prototype. It's available on SourceForge. It's open source code on the MIT license, so people can take it and embed it into their products. And it has two parts. For sending mail, you redirect all your outbound mail through a proxy. And the proxy just listens for mail coming into it, and it decides, oh, should this mail be encrypted or not? If it should be encrypted, it does the encryption thing and hands it on. Otherwise, it just hands it on to your regular outbound mail server. And then on the receiving side, well, we've got to generate a key set. We've got to be able to publish that into the cloud so that other people can send us those nice encrypted email messages. And that set of task functionality is handled by a program called the Key Manager. The Key Manager and the proxy are encoded as web services, and all that we need to define at this point are the interfaces to those web services. Because there's going to be different ideas on what should go in that cloud thing. I've got a set of ideas, but other people have other ideas of what should go there. What we're going to define in the plumbing is not the services themselves, not how they do it, but we'll describe what they're going to do and how we're going to talk to them so that they get the right messages. And the way that we do this in the modern infrastructure is using something called a web service, which is simply an application protocol that is layered over the HTTP protocol, or the web protocol, as it's also known. That's our interface to the cloud. When we first started drawing the cloud on diagrams like this, it was kind of like, oh, all this stuff is going to happen, I don't really care, where I'll just draw this, And you draw a cloud-shaped object. Today, the cloud is, it's a physical object, it's a real space. And it really comes from, well, I don't know what's going on there. It's some cloudy thing. The whole point of this project is to provide people with secure email that is just as easy to use as regular email. And so the first thing I need to prove here is that it really is going to be very, very easy to send secure email. So what does the user have to do? The first thing a user has to do when they decide that they're going to use secure email is to generate a key set so that people can encrypt messages that they're sending to them. And so the first question is, how does the receiver configure their email client? The key manager, as it currently written, only requires the user to provide one piece of information, and there's a second optional piece of information that it can provide in addition. The user has to provide the email address that they're generating this key set for. So if Bob's generating a key set, he needs to give his email address as bob@example.com. There is also an option to provide the address of a crypto advisor. And this is going to be some party that's going to help Bob publish his email address, publish his keys associated with those addresses, and maybe perform some trusted third-party services on Bob's behalf if Bob chooses that to do. Now, in the traditional S-MIME email world, you had no choice but to go through a certification authority who was the gatekeeper and the tool both for using secure mail. We don't want to make that mistake again. But we also don't want to make the same mistake that PGP made of having no option for somebody to step in there and say, okay, you need some help, I'll get you online, I'll do it. Because at the end of the day, what matters is giving people the ability to exchange secure email. And some people are technologically sophisticated enough that they can configure their email securely for themselves. Other people are going to need a small amount of help, and if they need a small amount of help, there will need to be a business model to support that. You run the key manager, and it returns you two pieces of information. One is a recovery code that is kind of like your get out of jail free card if you ever need to regenerate a new key set. This is going to be the thing that allows you to recover your private key should you need to do that. It's also going to give you a strong email address, which is something that I'll come to in a little moment. The next part of receiver configuration is, well, what if the receiver has more than one device? I can generate a key pair set on my main desktop machine, but what if what if I'm out and about and I want to generate keys so that I can use them in some mobile device that I'm carrying with me, my iPhone and all that stuff? In that case, I need to be able to transfer my private keys into this device so that I can have one encryption key that is published, that anybody who's trying to send me an encrypted mail uses the same key, and then I can read those messages on all the devices, all the phones, all the desktops, all the laptops, or whatever I may have. And so we need to be able to add a device. Today this is a little clunky because the tools are currently designed to work with absolutely no infrastructure support at all. And so the way that we do it is essentially we recover the key into the new device. But essentially what has to happen there is that the user is going to run the tool on the device. They're going to say, is this a device I want to be able to configure other devices from, or is something that I'm going to be walking around with, a device that is quite likely to get lost. I probably don't want to allow, if I lose my iPhone, I probably don't want to allow the person who finds it to sign up new devices to my trust set. So I'm probably not going to nominate that as a master device, but I might well nominate my desktops and have more than one of them nominated as a master device. And so I want to use my iPhone to read my mail. I'm going to go to my master device and say, okay, approve that iPhone, allow it to accept encrypted email. We've got to deal with events like removing a device. Say I get a new iPhone and I'm selling the old one on eBay. I don't want the buyer to be able to read my encrypted email, so obviously I'm going to delete all my private keys from the device, but I probably want to go a few steps further so that I'm absolutely sure that they can't be recovered, and generate a new encryption key, distribute it out to all my devices that are active so that none of my future email would be visible to the old device, even if the user could somehow recover the key from it. Now, I mentioned strong email addresses earlier, and the idea here is to take an idea from PGP of the PGP fingerprint and use it to create an email address that I can use that forces the use of a particular encryption key. So let's start from the top. If somebody specifies a traditional email address, Bob's sending a mail message to Alice. If he types in alice@example.com, the proxy, or the mail client if it's prison proof aware, is going to try to send the message encrypted if possible, and if the receiver has said always send, I prefer all my email to be sent encrypted. So you type in alice@example.com, and we're going to do what's called opportunistic encryption. We're going to encrypt if we can find a key and the receiver has said please send mail messages encrypted. But we also want to allow the sender to force the use of encryption, so that if the proxy can't find a key, it will say, oh, you said this must be sent encrypted, I can't find a key, so we're not sending that mail message. And that's the sort of thing that a doctor or a lawyer might when sending messages to a client, to make sure that those messages go encrypted or not at all. And here we're using a slight hack in that a question mark is a perfectly legal character in an email account part. That's the first part of the email address. The bit before the @ is the account part. But it is not a valid character in the username of any current computing platform. And the reason for that is that there's a database language called SQL that uses question marks as command, and you really don't want to have people generating usernames that could be SQL commands, because that allows them to do really bad things called SQL injection. So we're using the fact that an email address is permitted to have a question mark in the standard, and therefore all the address books that are out there that are compliant with the email specifications allow you to put a question mark in an email address. But in practice, nobody uses a question mark in their email addresses, and so we can hijack that character and use it for our own purposes. And what we're using it for here is to say, if you put the question mark at the front of an email address, it says, send this email if and only if you can send it securely. And now the doctor or the lawyer can use that address to make sure, okay, when I'm sending the patient data to Alice, I want to make sure that it goes, but only if I can get it end-to-end encrypted. And then finally, there is the strong email address, where we take a fingerprint, which I'll come to in a little while, and put that in front of the email address, again with the question mark as a separator. And this means only send the mail message if you can encrypt it under an encryption key that is validated under the specified fingerprint. So how do we do this? Well, we have some easy choices and we have some harder choices. Let's do the easiest choice of all first. There are over 2 billion email clients out there that support the S-MIME encryption format. So if we use S-MIME as our encryption format, we don't need to do any changes to the mail client at all to be able to receive encrypted mail, decrypt it and present it to the user. And so using S-MIME as the mail format is just a no-brainer. Our alternative choices are the traditional PGP format, which is widely used in PGP, of course. And that's the one that you see the begin PGP message, end PGP message. The problem with that particular format is that it predates MIME, which was the ITF standard that allows you to do attachments in email, to put images in email, HTML and so on. There's an extension to PGP called PGP MIME that supports those attachments. Unfortunately, it's not as widely used or supported. It didn't really get the same degree of attention and shakedown as S-MIME did. So if we're going to converge on one single format, S-MIME is the one to choose as the convergence format. We can support PGP format as a message format in the tools as a legacy transitional system, but S-MIME is the format that is the no-brainer format to go forward. But having chosen S-MIME as the message format, we're not now obliged to choose to make all the other decisions based on S-MIME. We can turn this into Frankenstein's monster. We can take a piece from S-MIME here, a piece from PGP here, a piece from PKIX here, and we can merge them all together. Each time we're going to make the choice that makes the best sense with respect to the functionality we're trying to deliver and the legacy infrastructure that we can leverage. So even though we've chosen S-MIME as the message format, we're also going to choose PGP, or at least a part of the PGP model, as the trust infrastructure. Now you're probably thinking, but you said that you were going to do trust infrastructure later. Well, that's true. We're going to do trust infrastructure in part 4, and my proposal isn't going to be the only one. But there's a second type of trust that doesn't require any infrastructure at all, and it's called direct trust. If I meet you in person and I give you my PGP fingerprint, you can then send me an encrypted mail message under that fingerprint, and I can read it, and you can be absolutely sure that you are talking to me, unless of course I've done something careless with my PGP key. And this is a feature that I believe that we should have in the new secure email system, in that if you've got the opportunity to use direct trust, you should make use of it. And so we should support the use of fingerprints. But since we're not using the PGP message format, we don't necessarily need to use fingerprints directly. And since we want to change the usability and make secure email more usable, we need to add in some more functionality. This turns out to be a really great place to add that functionality. And so when we get to fingerprints in the PPE sense later on, they're going to be slightly different from PGP fingerprints because they have more functionality. But we're still going to grandfather the old PGP fingerprints where they exist so that people can make use of them. Again, back to the Frankenstein model. We've got a direct trust model. We also want to allow people to make use of third-party trust where it already exists. There are already several million X509 v3 PKIX email certificates that have been issued. Komodo has 155,000 paid email certificates that are currently valid, and another 155,000 free certificates that are valid. Now, that's a sizable user base that we should build off rather than just tear down and try to start from scratch. So where we need a third-party trust model, we should just use PKIX. No need to reinvent the wheel. The big difference, though, from traditional S-MIME is we're not going to insist that it has to be PKIX or nothing. The big mistake of S-MIME was that they said you had to get a certificate from a CA or you can't do secure email. That's unsustainable because the people who are most interested in using secure email are people who are individuals who really are very sophisticated about cryptography, they don't see the need to pay a CA. And so CAs were set up as toll booths for a road that was never built. That's not necessary. The new secure email standard should support the use of PKICs for certificates, but should not require them. In the testbed protocol, I have this cloud that has the trust infrastructure that we're going to discuss in part 4, or rather discuss one option for in part 4. How do we connect to that? Well, I mentioned web services earlier. What sort of web service? There's a lot of choices there. Well, modern the industry has come to a convergence here and decided that web services should be encoded in a standard called JavaScript Object Notation, or JSON, and exchanged over HTTP. The reason that the industry is converging on JSON is that it does everything that its competitors do. It does everything that XML or ASN1 can do, but it is dramatically simpler. It has a lot less complexity, the code is a lot simpler, and therefore less likely to have errors, much cheaper to write, and there's ubiquitous support for it in all the platforms. We've taken some easy choices off the table, but that's left some gaps. And in particular, we've not said what the web services are going to do or how they're going to do it. We're not going to address how those web services do their job now. That'll be in part 4, and that'll be for other people to decide. What they do, however, is in scope for the plumbing, because the plumbing needs to know what they can ask the web service to provide. The 3 web service functions are public key discovery, public key validation, and private key management. Discovery and validation sound like they're the same thing, but there's a very important subtle difference. With public key discovery, Alice is sending a message to Bob. Alice asks the service, what's Bob's public key? The service comes back and says, here's a public key that you can use for Bob, and then Alice, her email client, checks to make sure that that is a key that she considers trustworthy. And the service may provide a set of information that helps Alice to make that decision. In public key validation, Alice just says, I'm going to be sending a message to Bob, you just tell me, and I'll trust you. And the service responds and tells Alice what to do, but Alice doesn't try to check it locally. She just goes ahead on what she's been told. Why would you want to have that system rather than checking your service? Well, it all depends upon what type of client you're writing and how much information you have available in the client to make that trust decision. If your trust decisions are very complex, you may not have enough information in the client to make a suitable trust decision. And so sometimes it's better to have a validation service rather than a discovery service. We're also going to be using the web service to provide some private key management, in that when we're trying to move keys from one device to another, we need to have some mechanism that allows us to move those bits in the way we want. So for public key discovery and validation, we're going to be using a protocol called OmniBroker that I've been working on for over a year now, and that's based on a much older protocol called XKMS, which I worked on with some folk in the World Wide Web Consortium. In XKMS, you would ask questions like, give me the key to send an email message to Fred. In OmniBroker, you ask a broader question of, tell me how X should connect to Y to do Z. And this is a very general question of, give me the IP address, give me the protocol to use, give me the version of the protocol, give me the keys to use, give me everything. And so in this case, The sender is Alice at example.com, the receiver is Bob at example.com, and the protocol is SMTP, which is the mail protocol. So a very high level service, and making the question at such a high level allows the service to provide a much more detailed answer. And the answer might be, well, don't use SMTP, use this whole new email protocol that has a different security model instead. Okay, so far we've been talking about the service, but we've not talked about how the service gets the information to make those policy decisions. In that the service can only say, send email to Bob using this key, if there is some information out there that tells it what Bob's key is. And that information ultimately needs to come from Bob. So we need a way for Bob to be able to say, here's my key. And we need a way for Bob to be able to say things like, I prefer all my email to be encrypted because I can read encrypted mail on all my platforms. So we need some way of knowing Bob's security policy, which means that we need a way for Bob to be able to publish it. And to do this, we use a privacy hardening block, or PHB. A PHB is a description of a security policy, so it's going to tell somebody, tell an email sender which public key to use, which formats, which protocols, and what circumstances the policy applies in. In that the email recipient might have multiple policies for different people and for different circumstances. I might have a policy that says, send all my mail encrypted under this key, unless it's really ultra duper super encrypted confidential, in which case use this key, which I don't put on devices that I might lose. So what is a fingerprint? And you'll notice that I've changed the spelling to PH. Well, that's because I'm changing the specification slightly from PGP, and so I don't want people confusing fingerprints that I'm using with the PGP fingerprints. So a fingerprint is the digest of a public key that is used to sign PHBs. Unlike in PGP, where a fingerprint is a fingerprint of a key that can be used for encryption or signing or whatever, in this system, we only use fingerprints for the public keys that are used to sign the privacy hardening blocks and nothing else. And making that a requirement allows us to make a series of simplifications in the infrastructure, because they know that when they're dealing with a fingerprint, they're going to always have to resolve that to the signing key of a PHB, and then they're going to have to pull a PHB, and that is going to tell them what to actually do. And the fingerprint is, of course, the component that we saw in that strong email address earlier. That's what we use when we want to say, send this email encrypted under this particular policy or not at all. Fingerprints can be reasonably short. We're using a strong cryptographic digest algorithm. It's actually SHA-2 512 bits, but we can truncate it to 128 bits securely, because security is a property of a system and not a technology. If you're designing a digest, the work factor of a digest function is set by the square root of the number of possibilities that it has. So if you have a 512-bit digest function, there's 2 to the 512 different possible digests, but your work factor for certain attacks is only 2 to the power 256 because of something called the birthday paradox. But that is a security property of an algorithm. The security of our system only depends upon the difficulty of an attacker being able to duplicate our particular fingerprint. And what that means is we don't need to have 256 bits of security to get an acceptable degree of security. We only need 128 bits. We can shorten our fingerprint to 128 bits and get a very good more than sufficient degree of security without unnecessary inconvenience. Okay, we have a fingerprint, but in order to send encrypted mail, we have to have a PHP. How do we do that? Well, the strong email address gives us a fingerprint value, which is 128 bits encoded. We're going to extract the domain part from that strong email address, and that is going to tell us the address of that tells us the address of the email service that we can send it to. It can also tell us the address of a web server where we can resolve that fingerprint to a PHP by applying a template, essentially, using the network information, the NIE standard, that essentially just maps HTTP URLs to, just maps digest values to HTTP URLs. Okay, well, what if you have an email provider like gmail.com that doesn't support this? Well, we'll just have to add another domain into the fingerprint somewhere so that there's a way of resolving it to a PHP. What if we don't even have a fingerprint? What if Alice is trying to send email to Bob and she doesn't even know if Bob has a fingerprint? Well, we can't do that in the direct trust model. And what we're talking about in this part is the direct trust model. Fingerprints are designed to support direct trust without trusted parties. If we are trying to send mail and we don't have a trusted third party, we're going to have to use one. We're going to have to use a trust infrastructure. And that's why part 4 is necessary. Because there's only so many people that I'm going to meet in person and can exchange trust with and fingerprints with directly. Now, what might be counterintuitive or objectionable for some people is that it turns out that the indirect trust model can, in certain circumstances, be stronger. And the reason for that is, if you have a trust infrastructure, you can deal with exceptional events much more conveniently than you can in a direct trust model. If all you have is direct trust to provide trust, well, all you got is direct trust to remove it as well. So I meet you in a bar, we exchange fingerprints. You then lose your phone that has your email encryption key on, your email decryption key on. There's no way that I can know that you've lost your phone in the direct trust model unless you meet me a second time and tell me and give me your new fingerprint. And so even though a indirect trust model requires us to depend upon some other third party in some degree, there are certain circumstances in which it's actually a stronger trust model because it's more robust rather than the direct trust model, which is extremely strong but can be brittle. Another problem with the strong email addresses is that they're just plain ugly. They're not memorable. Nobody's going to remember their strong email address like they remember their social security. But maybe that doesn't matter because modern email clients do a pretty good job at hiding email addresses from people. In fact, in many ways, they do too good a job. At this point, the sender side is complete. We've done all we need to be able to send encrypted email. How do we now configure the client to receive? Our functional requirements are all to do with managing this private key. And here, generating a public-private key pair is easy. The problem comes up, what happens when an exceptional event happens? What happens if a user loses it? What happens if they have multiple devices and they want to move the private key between them? And how often should we change them? Are encryption keys something that we should set once and use forever? Or should we change them on a regular basis, like every 2 months, or maybe every week, maybe every day? In the testbed prototype, this is all work that is done in the interface between the key manager and this infrastructure that we're about to generate. And to do this, we're applying principles that come from the certificate authority world, where we manage keys in a paradigm called online-offline keys. We have, ideally, the user is going to generate their master key, the key that corresponds to their fingerprint, and keep it in a device like this that isn't on the network, doesn't need to ever touch the network. And so the key can live here, the device can be put in a safe when it's not being used, and so that device is then rarely vulnerable to attack. So we minimize the attack surface of that key. We only ever use that key to sign our encryption key that we put in an actual device. So we use this key in the offline device, and we use this to sign an encryption key so that we can use it in our phone, in our desktop, all the devices we use every day. And since we want to be able to read the same encrypted email on all our half dozen, maybe a dozen devices, we're going to have to be able to transfer that private encryption key out to multiple devices. So the master key is never used for encrypting or decrypting. It's only ever used to sign certificates that say this is an encryption key that you can use for the next month or the next week or whatever. We're also going to put a signature key into each device, and each device is going to have a unique signature key. And these keys could in principle be used to sign contracts, sign emails that we know it's coming from the user. But we're also going to use those signature keys to identify the device when we're refreshing our encryption keys. So whenever the encryption key is changed, we generate a new encryption key, and the devices are going to authenticate themselves to the master system and say, okay, I need a new key, I need the new encryption key, encrypt it to me. The master key life cycle is fairly straightforward actually, because we use it fairly infrequently. When it's created, we're going to generate the key pair, and we're also going to generate a key recovery block. This is going to be the private key encrypted, so that when we want to, if this device gets lost or stolen or whatever, we can recover it. And we're going to give the user a recovery code, which is the encryption key for that recovery block. And this is going to be something that they can print out, put in a safe. I'm a big fan of keeping really important information in printed form rather than on electronics, in that floppy drives can die after a year, after 10 years, 20 years, whatever. Paper is a lot more robust. And then the recovery block is going to be archived somewhere. It might be on a floppy disk, it might be printed out, it might be stored in the cloud. But it's encrypted, so the storage of the recovery block doesn't really matter, so long as we can be very confident of getting it back if we need it. We need to be able to transfer the master key from one device to another on occasion, and at some point we may need to generate a new master key and hand over to a new. At the moment we use the public key encryption algorithm of choice is an algorithm called RSA, and the recommended strength is 2048-bit minimum. In the future, it's likely that the recommended minimum will go up to 4096 bits, and we might start using a algorithm called elliptic curve. At this point, it's a bit soon to start moving away from RSA. And so it's too soon, and so we want to use that. But if we ever move to elliptic curve systems, we need to be able to generate a new master key. And since these are personal keys belonging to humans, and humans are mortal, we've also got to consider what to do when the key holder dies. And that we want to be able to send out a message that says, don't trust this key anymore, without requiring the survivors to reconstruct the key. This is like when the Pope dies and they smash his ring up. You don't want them to be able to sign a few extra paper bulls when they're destroying his ring to show that it can't be used again. You want to be able to tell people don't ever trust this key again without that process causing the use of the key. It's fairly straightforward from a cryptographic point of view, provided that that requirement is anticipated. We also have a life cycle for device keys. When we add a device to our trust set, we've got to be able to authenticate the request, we've got to generate a new signing key for every device, and we've got to import the decryption key into the device so that it can read the messages. When a device is removed, we need to be able to say, yes, I've deleted all the keys from this device, it's no longer in the trust set, you don't need to send me any more information. And finally, we need to have some means of doing key refresh, in that if I sell this phone on eBay and it has at any time in the past had my private keys embedded on it, I want to be able to tell people, use a new decryption key, use a new signature key, don't trust those old ones. The key management doesn't absolutely need a web service, but having a web service there makes it a lot easier and a lot more convenient. So what we want the web service to be able to do is to archive the encrypted private key recovery blocks and to release them back to the user when they're needed. The other thing that we want the key management web service to do is to be the interface to these new and exciting trust infrastructures that we're going to talk about in part 4. So it's got to be able to accept assertions from the user, the key holder for publications, privacy hardening blocks, self-signed certificates, key endorsement. All that information that may be coming from the user needs to flow through to the outside world through the key management web service. So in summary, we've been talking about a lot of moving parts in this presentation, but we've not actually been talking about a lot of code. In the prototype implementation, the number of lines of code has increased and decreased over time. It's never been over 10,000. At the moment it's about 5,000 for the key manager and the proxy combined, and I'm trying to reduce that all the time. To receive encrypted email, all the user needs to do is to run the key manager program, give it their email address, and the key manager will then generate their key set, do all the work for them, publish them, and configure their email client. Or some future version will do that configuration automatically. At the moment, you have to follow some instructions that are rather more complex than they need to be. And then to send encrypted mail, you just send it as normal. The only thing that a sender ever needs to be aware of is when they want to force security policy, either say always send it encrypted or always send it encrypted in a particular way, then they're going to have to use a strong email address. So I believe I've proved, therefore, that frictionless strong email is entirely practical. We can have secure email that requires absolutely no more effort than traditional email. And that's a pretty important result. We have code and we have a current prototype. The current prototype is compatible with virtually all the existing email clients. It works with Outlook, it works with Outlook Express, it works with Thunderbird, it works with Apple Mail. Any email client that supports S/MIME can send and receive encrypted mail using the new system without any changes whatsoever. You can use your 10-year-old version of Outlook. And that's the advantage that comes from using S/MIME as the mail format rather than choosing PGP. Sending your mail encrypted when possible requires absolutely no more effort. The configuration, on the other hand, yes, it does need some usability improvement, but that is something that can be worked on. So the next steps, The prototype is, at this point, it's demonstration quality. I'll be working on it over the next few weeks to try and getting up to an example quality, something that people can start to do alpha testing on. The code is all on SourceForge, it's open source, and the proxy is written in C. The key manager is written in C#, which is an object-oriented version of C from Microsoft, but it'll run on Linux and OS X if you run under Mono. This is an area where we really need help. If you want to get into cryptography, if you're interested in email security, implementing strong email encryption could be a good way of getting some experience. At the moment, the proxy is a standalone client, but that's really functionality that should be embedded in the email clients. It should be embedded in Thunderbird, it should be embedded in Outlook and the mail clients that will accept extensions. On Android, we don't currently have a good open source email client that does SMIME, at least they don't provide one with the Android build. That would be another area that would be very good for somebody to get going with. We do, however, have some remaining questions, and these are the questions I'm going to be trying to answer in part 4. How do we do public key discovery? How do we do public key validation? And to do this, we have to venture into trust infrastructure. And this is the point at which my answer may not be the same as your answer. And that's okay, because my problems may not be the same as your problems. But what I'm trying to lay out here is not a solution that is the be-all and end-all solution for all time. I'm trying to provide a set of plumbing that multiple researchers can use to build on. So, if it turns out that all that we do secure email and all we ever use of my stuff is the plumbing, well, that's fine. Or alternatively, if people look at my plumbing and start to say, well, yes, that's okay, but we should do that this way or whatever, that's also fine. But let's get started. We've been using email now for a quarter of a century, and it's a critical part of the internet infrastructure, which means it is a critical part of the global infrastructure. It is an infrastructure we're depending upon for global commerce, and it's an infrastructure that we should be securing. And so I hope you stay for part 4 so we can discuss the trust infrastructure. In the meantime, I'd really appreciate it if you like my video, which I believe is here, and subscribe to my channel. Thank you very much for your time, and please stay tuned for part 4. Thank you. The use of a wheel.